Are you able to see the whiteboard? Hello?
Yes, sir.
Okay. In the last class, I defined a topological space, right? If X is any non-empty set, then we define when this X becomes a topological space. It has to satisfy topological space. It has to satisfy three conditions. Number one, the empty, First of all, you must have a subset tau of power set of X, okay? You are starting with a non-empty set capital X, and out of this, you get the set of all its subsets called power set of X. And for power set of X, you take a subset tau, okay? Now, we would like to define this tau to be a topology. So for that, this has to satisfy three conditions. Number one is that the empty set and the whole set must be members in tau. Okay, X and phi are different. These two distinct sets must be elements in tau. Tau is a certain collection of subsets of X. Hello. Number two, tau must be closed under finite intersections. Okay, means if you take finite number of entities from tau, their intersection must again be in tau. Okay, intersection gi equal to 1 to n must be in tau whenever these gi's come from tau. Okay, this is what we mean by finite intersection, closed under finite intersection. Number three is that this tau is closed under arbitrary unions. Tau is closed under arbitrary unions. Means you take any arbitrary collection of subsets from tau. Okay, let G lambda belongs to script lambda, be a subcollection from tau. Right? Let these G lambdas come from tau. They may be uncountable or countable or finite. Okay. Then if you have union G lambda belongs to big lambda. If this belongs to tau, then we say this tau is closed under arbitrary unions. Okay, so means you are taking an arbitrary collection of sets from tau, and if the corresponding union of them is in tau again, then we say tau is closed under arbitrary unions. Okay, it is closed, right? These three properties together make this tau a topology on capital X, and we say X equipped with this tau is a topological space. Okay, this is what we mean by a topological space. And in the last class, we looked at various examples. Right? We looked at various examples of topological spaces. The first one is that, right? The tau in discrete topology. This consists of the empty set and the whole set. If X is any non-empty set, then you have a topology on capital X. It is in discrete topology. It consists of these two elements. And the topology is the discrete topology. It consists of the whole power set of X. Okay. And then we looked at co-finite topology, co-countable topology, and so on. Okay. Today, I want to discuss a characterization of a closure, right? A path bar. Okay, this is called a closure, right? Closure of A. We read closure of A, or we also say a closure. Here, you let X be in it. Let X comma tau be in a topological space, right? And let A be subset of X. Let A be subset of X. For A, we'll define a closure. Before defining this, I want to recall what I mean by an open set, right? Let X comma tau be a topological space and A be a subset of X. Let G, let G be a subset of X, right? We define G is open if and only if When do you say a subset G of a topological space X is open? Hello? Hello? Anybody?
Yes, sir.
Yes, sir.
If you have a topological space X, and if G is subset of X, when do you say G is open? What do you mean by that? G is open? G has to belong to tau, isn't it? Isn't it? If you have a topological space X comma tau, and if G is subset of this whole space capital X, and this G can be called an open set. G can be called an open set if and only if G is a member of tau. Okay, this is definition. This is the definition. Means we are naming all the elements of tau as open sets. By open sets, we mean that there are elements in tau. Okay, right? And then once we know this, for example, if you take the indiscrete topology consists of the empty set and the whole set, right? And so therefore these two are open sets because of the definition of open set like this. Okay, these two are members of this tau, and therefore these two are open sets in indiscrete topology. And here, if you come to discrete topology, this is discrete topology. Every subset of X is an element here. Every subset of X is an element here, right? Therefore, every subset of X becomes an open set. In the discrete topology, every subset of X becomes an open set, right? Then we define what we mean by closed sets, right? And let F be a subset of X. We define F is closed if and only if its complement is open. Its complement is open. Okay. We define closedness of a set in terms of the complements, in terms of its complement. Okay. Let F be any subset of X. We say F is closed if its complement, F complement is open. Right? What do we write? If we write like this, F complement belongs to tau means F complement is open. Right? This is definition. This also is definition. Okay, this is how we define closed sets in a topological space. Therefore, using this definition, right? We have that phi and X are open in this indiscrete topology. Phi and X are open. Okay, because they are members in this tau. And what is phi? What is phi complement? What is phi complement? What is complement of phi? It is X minus phi. Complement means X minus phi. It is X. Okay, complement of phi is X. And because phi is open, so X will be closed. Okay, because phi is open, its complement will be closed. That's how capital X is closed. So, sorry, capital X is open as well as closed. So in this topology, in the indiscrete topology, capital X is closed as well as open. Okay, so capital X is closed, and open. Such sets are called Clopen sets. Clopen sets. Clopen is an abbreviation for a set which is both open and closed. Right? Clopen set. Okay, so capital X is closed in the discrete topology. Similarly, if you look at the complement of capital X, what is complement of capital X? X minus capital X. What is this? What is X minus X? It is empty set. So, right? Capital X is open, therefore phi is closed. Capital X is open in discrete topology. In fact, in any topology, these two sets are open sets. So if you, and its complement is phi, right? Because capital X is open, its complement becomes closed. Therefore, phi is closed. So phi is open as well as closed. So empty set is also a Clopen set, right? It is open and it is closed. Therefore, empty set is also closed in this topology. In fact, these two sets are both open and closed sets in any topology. The empty set is both open and closed, and the whole set, capital X, is also both open and closed. Means every topology has got two Clopen sets. Okay. Yeah. And now let me talk about this discrete topology. What is discrete topology? What is discrete topology? Discrete topology is power set of X. Discrete topology is power set of X, right? If A is any subset of X, if A is any subset of X, so A belongs to power set of X. This implies A is in power set of X, and power set of X is the discrete topology, tau D. Okay, so if A is whatever Bx, if capital A is it's a subset, then it is in the set power set of X, means it is in tau D. Therefore, capital A becomes open. Therefore, capital A is open. Okay, what is capital A complement? A complement is X minus A, right? This also is a subset of X. X minus A is also a subset of X. Therefore, A complement is an element in power set of X. Okay. For this A, you look at A complement. It also is a subset of X. Therefore, it will be present in power set of X. This implies A complement is open. Because your power set of X is tau D. Your power set of X is tau D. This is discrete topology. Therefore, A complement becomes open, right? Because A complement is open, this gives you that A is closed. So capital A is open as well as closed. So in the discrete topology, any subset capital A is both open and closed. So in discrete topology, any subset of X is both open and closed. It is a Klopen set, right? In the discrete topology, any subset capital A of X is both open and closed. Okay. Well, now let us come to the definition of A closure. Hello, are you able to follow me? Hello. Hello.
Yes, sir.
Now,
Yes, sir. Yes, sir.
yeah. Now let us take X comma tau a topology as a topological space. For this X, let us take A to be a subset. Okay. Now I would like to define A closure. This is defined as intersection of F where F is closed, and F contains A. Right? If you are in a topological space, if you are given a topological space X comma tau, and capital A is any subset of capital X, then we can define A closure. If I write to this kind of equality symbols, it means defined. This is defined. So this is defined as intersection of all F's where F is closed and F contains A. Means the capital F is a superset. It is a closed superset of A. Okay. Means corresponding to this A, you collect all those supersets which are closed and take their intersection. Take the intersection of all of them. That is defined to be A closure. Okay. Right. So if you are given a subset capital A of X, then its A closure, its closure is defined as the intersection of all closed supersets of A. Okay. Right. Out of this definition, one property is obvious. What is that? Each F contains A. Therefore, this intersection contains A. Right. In this collection of F's, for this collection of F, each F contains capital A. Therefore, this intersection F, as that F is closed and F contains A. Okay. Because each F contains A, this intersection also contains A. Capital A is subset of each constituent set. Therefore, this intersection will again contain capital A. So A closure is a superset of A. For whatever be capital A, its closure is a superset of A. Okay, so that you have to notice, right? Yeah. Now we can characterize it. Okay. Before that, let me give you an example, and then we'll go to one theorem. I will collect from book. That is, yeah, example 2.4.2. 2.4.2 example. Okay. That is page 14. It is page 14, right? Capital X is 1, 2, 3, 4, right? And then tau is 5, capital X, singleton 1, singleton 2, and doubleton 1, 2. Okay. You can verify that this is a topology, and then let us take capital A to be 3, 4, right? And then, yeah, he is saying that A is closed. Okay. What is, he's saying A is closed. Let us see how. What is A complement? In this set, is this a topology? If you take the intersection of any two elements from here, right? Intersection of phi with any of these is phi. Intersection of x with any of these is that set itself. Intersection of these two is empty. Intersection of singleton 1 and this is singleton 1. It is present there, right? Intersection of this and this is singleton 2. It is present there. So finite intersections are present there. Arbitrary unions. The intersection of these two is this one, and the intersection of this and this is this larger one. And you can see that this is closed into arbitrary unions. That's how this becomes a topology. Okay. Now, is this capital A closed? To check something is closed, some set is closed or not, you have to look at its complement. What is complement of capital A? It is x minus capital A. So from this, you subtract this. So what do you get? You delete 3, 4, you get 1, 2. Okay. So A complement is the set consisting of 1, 4. The set consisting of 1, 4. Right? Right? A complement is x minus A. From this, you delete 3, 4, you are left with 1, 2. And this doubleton 1, 2 is present here. Therefore, it is, right? Therefore, it is an open set. This is an open set. So complement of A is open. Therefore, A is closed. Right? So that's how this set capital A is closed. Right? And then, you look at C. He has given C to be the doubleton 1, 2. Right? For this, let us find C closure. For the set C, let us find closure. Right? To find closure, we need to find all closure supersets of A. To find A closure, we have to find all closure supersets of A. So let us form closure sets. Let us form closure sets, right? Out of these open sets. You have to form the complements of all these. Complement of phi is x, complement of x is phi, complement of 1 is 2, 3, 4, complement of 2 is 1, 2, 1, 3, 4, and complement of 1, 2 is 3, 4. Okay. This is the set consisting of all complements of these open sets. So this is a collection of closure sets. These are all the closure sets in this topology. Okay. Now we want to find C closure. So you have to collect all Fs that contain C, right? Means you have to collect closure sets from here, which contain doubleton 1, 2. So doubleton 1, 2 is subset for capital X. And it is not subset for this. It is not for this, not for this, not for this. So it is intersection of singleton. It is intersection of one set, capital X. Intersection of one set is that set itself. So C closure is X. Therefore, right? For C is this one, and these are all the closure sets. You out of these you collect which contain this C, this doubleton 1, 2. There is only one element from this F which contains C. So that is capital X, okay, right? Right, and therefore intersection of X is that X itself. So that's how C closure is X, right? Therefore the closure of this set is the whole space consisting of 1, 2, 3, 4. And if you have this situation, if the closure of a set becomes the whole space, we say that set is dense. in this space. We say C is dense, a dense subset of the whole space. Okay. By a dense subspace, we mean there is a subset C in X as the C closure is X. Okay. So we say C is a dense subset of capital X, right? Yeah. So that's how for a given topological space, the subset of it, you can find closure. Okay. Now let's come to a characterization called a theorem. This theorem characterizes a closure. So, right, I'm assuming, yeah. So let X comma tau be a topological space and A be subset of X. Show that A closure is equal to small x belonging to capital X, such that each open neighborhood G of X intersects capital A. Okay. This theorem characterizes a closure. Right, we defined A closure to be the intersection of all closure supersets of A. This gives another equivalent form of A closure. A closure becomes the set of all points small x for which each open neighborhood G of X intersects A. Okay, if for this small x every open neighborhood G intersects A, you collect that X here. What do we mean by an open neighborhood? See, you are inside a topological space, X comma tau, and you have taken G. Yeah, you take an element small x. If there is a G containing small x, right? If there is a G belonging to tau, so that X belongs to G, we say this G is an open neighborhood of X. Okay, this is called an open neighborhood of X. I'm writing briefly. You have to write the full form. An open neighborhood of X. G is called an open neighborhood of small x in this topology. Okay, right? So if you are inside a topological space, if small x is an element in capital X, right? For this small x, capital G is said to be an open neighborhood if this capital G belongs to tau and that small x belongs to G. Okay, this should happen. So this small x should sit inside the open set G. In that case, we call G a neighborhood or a open neighborhood of X in tau or in this topological space. Okay. Now let's try to prove this. This question was asked in 2019. Okay, this was asked somewhere in 2019. Okay. To prove this, we proceed like this, right? We want to. This is one set for capital A. This is one set, and the right hand side is one set. We take right hand side to be capital B. Let capital B to be small x belonging to capital X, such that each open neighborhood. Let's go for some other color. Such that each open neighborhood G of X intersects capital A. Right? Let me name the set on the right hand side of this equality B. Right? By name B. Let me give a name capital B for this set on the right hand side. So we have to show this. A closure is equal to B. This is what we have to show. Okay. We'll use one technique. If you have to show a set D is equal to F, right? It is enough to show D complement is equal to F complement. Okay. To show D, two sets D and F are equal, you show that their complements are equal. Then this follows. So that's what we use this property. So to show that A closure is equal to this one, we'll go for the complements. Dealing with complements will be helpful in this particular theorem. So we wish to show that A closure complement is equal to B complement. Okay, so let small x belong to A closure complement. Right? Let us take an element from here and let us show that it is here. We'll show A closure complement is subset of this and B complement is subset of this. Right? To show two sets are equal, show that this is subset of this is subset of this. That way, to show these two are equal, we will show this is subset of this and this is subset of this. So let us start with an element in the left-hand side. Okay. So what does this mean? What does this mean? X is not in A closure. Okay. X is the complement of A closure means X does not belong to A closure. Okay. Now, can I do this, right? Now, yeah. What is A closure? What is A closure? Right? Or how did we define A closure? It is defined as intersection of F. F is closed and F contains A. Right? A closure is defined to be intersection of all closed supersets of A. Okay? This is definition of A closure. Now, X is not in this intersection means X is not present in one of the constituent sets. Okay? If X is present in all the constituent sets, it will be present in the intersection, but it is not present in the intersection. Therefore, X is not in at least one constituent set, capital F. Okay, so this implies there exists a F closed. F contains A, comma X is not in F. Okay. X is not in A closure means X is not in this intersection. Therefore, X is not in one of the constituent sets. So there exists one constituent set F closed. F is superset of A, such that X is not present in that F. Okay. Now, what does this mean? X is not present in F means X belongs to F complement. So this implies X belongs to F complement. Okay. And F is closed, therefore F complement is open. Right? F is closed, therefore its complement is open. So we have got an open neighborhood, F complement of X. So this is an open neighborhood. This is open neighborhood of X. Right? And how about, yeah, see, this F contains A. This F contains A. This is F and A is subset. A is subset. Capital A is subset. F contains A. F contains A. So what can you say about F complement? Where does F complement lie? F complement is this one. This is F complement. The yellow part is F complement. So F complement does not intersect A. F complement A are disjoint. Okay. So yeah, A is sitting inside F, and your right, A is sitting inside F. Red set is sitting inside black set, and F complement is yellow set, and yellow set and red set are disjoint. So means F complement and A are like disjoint. So you have F complement. You have F complement intersection A is empty. Okay. So this F complement is an open neighborhood of X, and that its intersection with A, the yellow part is F complement. Its intersection with the red part, A, is empty. So you have got an open neighborhood F complement of X, which does not intersect with A. This F complement is not intersecting. It does not have any common element with capital A. Okay, means it is not intersecting. It intersects means there is a common element, at least one, but it is not intersecting. Therefore, their intersection is empty. So F complement is not intersecting with A. So you have got an open neighborhood F complement of X which does not intersect A. Means this small x cannot be here. This small x cannot be here. This implies that X does not belong to B. Okay. So because B is this collection And you have got an open neighborhood G equal to F complement of X, which does not intersect A. So this small x will not be here. If small x will be here, every open neighborhood G of X must intersect A. But you have got an open neighborhood G equal to F complement of X, which does not intersect A. Violating this property, this criterion, okay, defining criterion of small x. Therefore, this small x will not be present in B. So you started with an element in the left hand side, and that element, and it is not in B means that element is in B complement. If X is not in B means X is in B complement. So you started with an element on the left hand side and it is in the right hand side. So this is subset of this. Okay. So therefore A complement closure, A closure complement is contained in B complement. Right? I started with an element here, X in the left hand side, that is in the right hand side. So this set is subset of this. So A closure complement is contained in B complement. Okay, and conversely, let us show that this is subset of this. So in the textbook, all steps are done together. For the converse also, they are clubbed with the previous part steps, but I am dividing to understand better. So let X belong to B complement. Let X belong to B complement. What does this mean? This means X is not in B. What does this mean? X is not in B means X does not satisfy this criterion. There exists an open neighborhood G of X which does not intersect A. Okay, while what is the negation of this? There exists, replace each by there exists. There exists an open neighborhood G of X and put not here, which does not intersect A. Okay, so this implies there exists an open neighborhood G of X such that G intersection A is empty. Right? X does not, I have taken an X here. So X is not in B. So X is not satisfying this. Means there exists an open neighborhood G of X which does not intersect A. Right? There exists an open neighborhood G of X which does not intersect A. G intersection A is empty. Yeah. Now, what do I get? Out of this G, I want a closure set. Right? G is an open set. So its complement is closed. So G is open implies G complement is closed. Okay, G is open, so therefore G is open G is open, therefore G complement is closed. And G intersection A is empty means what? G intersection A is empty implies what? Implies what? G complement contains A, is it? G intersection A is empty. This is Z, right? And say this is A. Let A be red one. Let G be this black set. Okay, G intersection A is empty. G and E are disjoint. So where does this A lie? It lies in G complement. The set red set lies in the complement of G. Okay, what is complement of G? It is this one. This is G complement. This blue part is G complement. Okay, so G intersection A is empty gives you G complement contains A. So I have got a closed superset of A. I have got G complement is closed. I have got a closed superset of A. Now, what is A closure? A closure is equal to intersection F such that F is closed and F contains A. Right? By definition, A closure is this intersection of all closed supersets of A. Now G complement is a closed superset of A. So G complement is closed and G complement contains A. So G complement is one of these Fs. Okay. So yeah. And what else you have? X belongs to G. G is right. G is an open neighborhood of X means X belongs to G. This gives you that X belongs to G. G is an open neighborhood of X means X belongs to G. So X is not in G complement. X is here. X is in G. X is here, somewhere here. That is X. So X is not in G complement. It's not in the blue set. So you have X is not in G. complement. Because X is in G, because X is in G, X is in this black set, X is not in blue set. It is not in G complement. Now, G complement is one of these Fs, okay? This is closed, right? This is closed superset of A. Closed set and contains A. Closed superset of A. Okay? X is not in G complement, which is a closed superset of A. So X is not one of these Fs. X is not present in one of these Fs, so it cannot be present here. It is right. This G complement is one of the constituent sets, and it is not present in this particular constituent site. Therefore, it cannot be present in the intersection. Therefore, X will not be present in A closure. Okay. So we started with an element here, and it is not present in A closure. Means what? It is present in A closure complement. I took an element X on the right hand side, and ultimately I got X is not in A closure. Means X is in A closure complement. So X is present. Yeah. So X is present in A closure complement. So I took an element here. I showed that it is in the left hand side. Therefore, A complement. Therefore, B complement is a subset of A complement, A closure complement. Therefore, B complement is contained in A closure complement. Okay, right? This is subset of this, and this in turn is again subset of this A closure complement. So if you combine these two, you will get that A closure complement equal to B complement. Okay. So if you give a number for this, this and this give you that B complement is equal to A closure complement. Will give you that A closure complement is equal to B complement. Okay. So from here, so these two sets will be equal. Reverse inclusion is also correct. Okay. Therefore, equality holds between these two sets. And now you apply complement again. You will get A closure equal to B. Okay. So that's what you have. Right. So when this closure of a set capital A can also be visualized as set of all points X whose every neighborhood intersects A. Okay. This is another criterion or characterization of the closure of A. Okay. This is important in exam point of view. Okay. Next, I would like to do the next question, that is in the 2019 paper. That is from the next unit. Suppose X is a second countable space. Yeah. 1B. Suppose X is a second countable space. Second countable space. Right. If a non-empty set G in X is union of G alpha, alpha belongs to delta of open sets. If G is equal to union G alpha, alpha belongs to delta, right? Where G alphas are right, coming from are open in X, okay? Are open. Then G can also be written as a countable union of G alphas. Okay. So here this is, in fact, this property has a name. It is called Lindelof theorem. Lindelof theorem. This is from third unit. Lindelof theorem. Lindelof's theorem, right? Okay. Capital X is a second countable space. If G it can be written as a union of certain open sets, then G can also be written as a countable union of these G alphas. Okay. First of all, let me explain to you what is the meaning of second countable space. For that, you need to understand the concept of base. Okay. say you have a topological space x comma tau, right? And then, hello?
Yes, sir. Listening.
Are you able to follow me?
Yes, sir. Yes, sir.
Okay. If you have any difficulty, you must ask.
Yes, sir.
Otherwise, I assume everything is clear. Okay. This is a very bad time. I don't know how you people are bearing since morning. Okay. Right. This is a very large dose of mathematics for you today and tomorrow. Okay. Yeah. Let this be a topological space. Let this be a topological space. Okay. And then let script B be a subset of tau. Okay. Right. Yeah. Let G be any open set. Okay. If you can write this G as a union of set of members of script B, then we say this script B is a base. Okay. This G is any arbitrary set. Any arbitrary open set in this topology should, if it is writable as a union of certain members of script B, we say such a collection script B is a base. Okay. Let G be belong to tau. If script G is equal to union B lambda, B lambda belongs to script B, right? For lambda belongs to certain script lambda, right? If you can write G as union of certain B lambdas coming from script B, then let this is arbitrary. G is in an arbitrary set. Okay, it is an arbitrary open set. Right? If this arbitrary open set G can be written as union of certain collection of elements from script B, then script B is called an open base or base, simply base for tau. Okay, right? You're starting with a topological space x comma tau, and for this tau, you take a sub collection of open sets. Right? We want script B to consist of certain open sets, right? And GB, capital GB, any arbitrary open set. And you can, if you can write G as union of certain elements from script B, they may be infinite in number and sometimes uncountable also or countable, right? If you can write G as union of elements from script B, then the script B is called a base for tau. Okay, and this should happen. This expansion, this expression should be possible for every script G. If you vary G, this collection may be varying, but you should be able to write G as union of certain members from script B. Okay, right. And whenever this is possible, we say this script B is a base for tau. Okay, and you have to compare this with the, see, in linear algebra, you will be studying basis. In linear algebra, you'll be studying basis, right? If you have R3, right? R3 is the linear span of these elements, I bar, J bar, and K bar. It is linear span of these three-dimensional vectors. Okay, I bar is 0, 1 I bar plus 0 J bar plus 0 K bar. Okay, J bar is 0 I bar plus 1 J bar plus 0 K bar, and K bar is 0 I bar plus 0 J bar plus 1 K bar. Okay, these three are three-dimensional vectors, mutually perpendicular right-handed system of three-dimensional vectors. Okay, this linear span of these is R3. We know that this is a basis. The set consisting of I bar, J bar, and K bar is a basis. Is a basis for R3, isn't it? If you express these as triplets, order triplets, you have 1 0 0 and 0 1 0 and 0 0 1. Okay, this set consisting of these three elements forms a basis for the set of triples in R3. Okay, right? and there we call this a basis. And we know that every element, if you take a point P from R3, P is what? P consists of an ordered, P is ordered triplet. This can be written as X into I bar, of course, X into 1, 0, 0. X into 1, 0, 0. If you take P bar, position vector P bar, then you can write it. This is X into 0, X into 1, 0, 0. X into 1, 1, 0, 0 plus Y into 0, 1, 0 plus Z into 0, 0, 1. Okay. Any general element P in R3 is an order triplet XYZ of real numbers XYZ. Okay, this can be written as a linear span of these three mutually orthogonal elements. Okay, right? And we say this is a linear span. P is a linear span of these three vectors, linearly independent vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, and we because of this possibility that this set spans this space R3, we say this is a basis. This is a basis for R3. Okay, right? And you have to convert these into the terms of set theory. Okay, this is what we do in linear algebra. But in topology, you will be replacing this by a topological space. You will be replacing this. You will be replacing this by a topological space x comma tau, and then a general element in tau is replaced by a general open set, and then this linear combination is replaced by unions, right? And these linearly independent vectors are replaced by basis elements. You bring in a basis, right? A some collection of tau, and these elements are some b lambdas, where b lambdas come from script b for lambda varying over a variable index set big lambda. Okay, so there is an analogy between linear algebra and topology. Okay, whatever you do here for basis, here we call this a basis, but here we call this a base. Okay, the terminology slightly differs. This is base. Okay, so here you have a topological space, and then you start with a subcollection of tau, right? For us, this is the topological space, and then we say this is a base for tau if any arbitrary open set G can be written as union of certain collection of elements from b lambdas from script B. Okay, so this is the analogy between linear algebra and topological space regarding the concepts of basis and base. Okay, you should not get confused, right? Yeah. Now, sometimes for some topological spaces, this base may be countable. In that case, we say that space is second countable. Okay. Before that, let me give an example, some examples of basis. Some examples of basis, right? In for R under usual topology, right? For R under the usual topology, under the Euclidean metric, you have usual topology. For this, a base is right. What is a base? You take open intervals a comma b, right? You take open intervals a comma b, a less than b, a, b are real numbers, right? This becomes a base for the topological space R under the Euclidean metric. Okay. In fact, this also is a base. You can take a comma b to be rational numbers. You can take a comma b to be rational numbers. A comma b such that a is less than b and a comma b are rationals. Okay, right? This also becomes a base. In fact, this becomes countable. This is countable. Okay. Q is countable. Therefore, this collection becomes countable. So R under the usual topology has got a countable base. Therefore, R is second countable. If you have a topological space with a countable base, such a topological space is called second countable. Okay. So R is The real line with the usual distance metric, Euclidean distance metric, is with the usual topology on it, is a second countable topological space. Okay. Now let us come back to this one. Yeah, this theorem, Lindelof's theorem. So we are taking X to be a second countable space, and if G is an open set, which formed of certain open sets, G alphas, out of these, what he says is that out of this you can leave uncountable number of things. You can choose only countably many number of G alphas, and still their union can be G. Means because of this second countability property, for G, you can deal out of these G alphas, you can deal with countable number of them only. Okay, that is the strength. That is the strength of this second countability. Okay, let us prove this theorem, Lindelof's theorem. Yeah, proof of Lindelof's theorem. Let X comma tau be second countable topological space. Means what? It has got, yeah, of course. And let us take G to be an open set which can be written as union of certain G alphas from tau. Let G belong to tau be such that G is equal to union G alpha. Alpha belongs to certain delta. Okay, where G alphas come from tau. Okay, let us take an open set which can be written as a union of certain members from tau, right? Yeah. Now we are saying this is second countable space. So by this assumption, this topology has got a countable base. Okay, second countability means this has got a countable base. So this implies that there exists a countable base, base. Script B is equal to V1, V2, V3, and so on, Vn, and so on for tau. Okay, because we are assuming that X tau is second countable. This topology has got a countable base. Let it be the set consisting of B1, B2, B3, and so on. Okay, right? Of course, this will be a subcollection of open sets. Each of these Bn's will be open sets because it is a base. By base we mean it is open base. So this will be right. Each Bi will be an open set. Now, right? Now, yeah. Let us take a small element X in G. So let small x belong to G. What is G? G is formed of union G alpha. Alpha belongs to script lambda. Okay. I'm taking an element small x in this G. So X will be in this union G alpha. Alpha belongs to lambda. I'm taking X in G. So X will be in this union. This implies there exists a G alpha for which X belongs to. So there exists an alpha K. Why alpha K? There exists a G lambda, otherwise there exists a lambda. There exists a lambda belonging to delta such that X belongs to G lambda. Okay. So in this index set delta, there will be some lambda. So corresponding to that, you look at G lambda, X belongs to that. See if X is in this union, it has to be in one of the constituent sets. Because it is in union, it has to be in at least one constituent set. Let it be G lambda, right? So there exists a lambda in big delta such that X belongs to G lambda. Okay. Now this G lambda is open. This G lambda is open. Each G alpha is open. Each G alpha is open, right? Each G alpha is open. So, right, G alpha is open. So you have G lambda is open. Now, from the definition of base, you have got an open set and an X in that. So, and we are assuming that this script B is a base. Therefore, there will be a B, there will be an element BK from this script B, so that script BK, that set BK will be in between X and G lambda. So since script B is equal to B1, B2, B3, and so on, Bn, and so on, is a base for tau. There exists a k, a natural number, which is one of the suffixes, such that X belongs to BK belongs to G lambda, okay, and BK comes from script B, right? See, this X is in G lambda and G lambda is open. And what is the definition of a base? If you have any open set, it can be written as union of certain members from script B. So if you take X here, right? If you take X here, if X in this set G, if you take X in this set G, right? If you take X in this set G, it will be in one of the constituent sets B lambdas coming from script B. Okay, so and this B lambda being one of the constituent sets, this B lambda is contained in G. So X belongs to B lambda is contained in G. So that's what I wrote. X belongs to B lambda is contained in G. It's something like that. So because G lambda is open, this G lambda is formed of certain basic open sets, means a set from base, and therefore it will be in one of those open sets, basic open sets. So from the definition of base, this comes. So X will be in BK, where BK, here I must use, this is a wrong symbol, it's subset of G lambda. Sorry, this should be subset. Okay. This is contained in G lambda, right? BK is contained in G lambda. G lambda is B lambda is contained in G. B lambda is contained in G. Similarly, BK is contained in G or G lambda. Yeah. In place of G, you have G lambda. So here I have BK. BK is contained in G lambda. Okay. So because of this, in between these two, there will be a basic open set BK. Now what you do is, you look at this collection. Let script G be defined as G alpha K such that there exists an X belonging to BK is sitting inside G lambda. Or G alpha K, right? Choose only one such G alpha K for every BK. Okay. See, now this is possible for every X. For every X in this capital G, you have a certain BK and certain G lambda. Now you look at this equation. This is not equation, it is an expression. You look at this expression. Now, out of all these, you look at this G lambdas, and there in some situations there may be more than one G lambdas. So for a single you fix BK, and for the fixed BK, there may be more than one G lambdas. You take only one G lambda for every BK, and that's what I have written here. There exists an X belongs to BK is contained in G alpha K. Choose only one such G alpha K for every BK. For every BK, out of these G lambdas, you take only one G alpha K. You take only one G lambda, call it G alpha K. You take the G alpha K here. Okay. The point is, for every suffix here, you are taking only one set. And now we know that script B is countable. For every suffix, you are taking only one set. This also will be counted. So this becomes countable. Okay. And also you have these conclusions. Small x is varying over G. So G will be equal to union of all these BKs, and it will be union of all these G lambdas. Therefore, G will be equal to union BKs, right? Where, right, as K varies, and this is equal to union G alpha Ks. Okay, as alpha Ks vary, as G alpha Ks vary over G. Okay, let me write that. Right. Where alpha Ks vary over G, where here G alpha Ks vary over G, right? You are taking these BKs, okay? So K in 1, the suffixes K or those of BK coming in this expression. Okay, so as X is varying in capital G, so G will be contained in union of all these. Okay, and this it will be contained in this union G lambdas. Union G lambdas will be contained in G. Okay, so this implies right, union singleton X, as X belongs to G, is contained in union BK, is contained in union GK, which is contained in G. Okay, so as X varies over G, union of all these singletons X will be contained in union BKs, and that will be contained in union GKs, and each GK is subset of G. Union of G lambdas will be contained in G. So because this is G, this is G, that's how G will be equal to union BK is equal to union G alpha K, right? I'm changing the name. I'm calling GKs as G alpha Ks. So G alpha Ks are coming from this script G. This script G is countable. So out of this union, we are able to choose countably many G alpha Ks such that their union is again G. Okay. So that's how the second countability gives us a countable base for the topology X. Right. Out of this countable base, every open set can be written as union of countable number of open subcollection of the given open collection. Okay, right? So this is the strength of the Lindelof's theorem, right? whenever in a countable topological space, you have any open set written as union of certain open sets. Out of these, you can take only countably many G alpha such that their union still will be forming G. Okay, you can write G, you can deal with countable number of these G alphas and make G and cover G. So that is the strength obtained from the second countability of capital X. Okay, this is the crux. This is the crux of the theorem. This is the crux of the theorem. This sentence is the crux of the proof of the theorem. Okay, so that's how we handle it. Next, we come to the exercise 2A. Exercise 2A in the same question paper. See, I am very slow in teaching, so I am depending on this question paper. I'm trying to explain you certain concepts, and you have to understand these. You have to practice these that I am doing here, and read something more also from the other important topics. Okay, so let F be a mapping from a metric space. Let F be a mapping from a metric space X into a metric space Y. Okay, then prove that F is continuous. F is continuous if and only F inverse of A is closed and X is closed in X whenever A is closed in Y. Whenever A is closed in Y. Okay. F is a mapping from a metric space into a metric space. Why? Yesterday or in the previous class, I was defining a metric space. Okay, and then continuity I did not define. Yeah, let me define continuity, and then we'll come to prove this. So what do you mean by continuity from a metric space into between two metric spaces? Hello? What do you mean by continuity between two metric spaces? Hello, is there anybody? Hello, 17 people are present. What do you mean by continuity between two metric spaces? In real analysis, you might have studied continuity between two metric spaces. See, if you take an x0 in capital X, what do you mean by continuity of f at x0? F is continuous at x0. What do you mean by this? You recall, if f is a mapping from a subset of real numbers into R, right? If A is a subset of R, if f is mapping capital A into R, when do you say f is continuous at A? If and only if f is continuous at A, right? F is continuous at A. Yeah. How do you define this? The limit f of A x as x goes to A must exist and must be equal to f at A, right? This is what you mean by continuity of a real valued function of a real variable, right? Limit f of x as x goes to A must exist and it must be f at A. This A must be a limit point of this set capital A. Okay. Yeah. Now, if your f is between two metric spaces, if your f is between two metric spaces, right? What is this in terms of epsilon delta? What is this in terms of epsilon delta? For every epsilon positive, there is a delta positive such that modulus of x minus a less than delta implies mod f of x minus fa is less than what? Epsilon. Okay. What you convert this into the terms of epsilon delta. For every epsilon positive, there is a delta positive such that 0 is such that mod x minus a is less than delta implies mod f of x minus f of a is less than epsilon. Okay. Here 0 less than mod x minus a will not be there. X can be equal to a because of continuity. Okay. Yeah, this is what you mean by continuity. All right. Now you will be see this is a metric. This modulus is a metric on A here. This modulus is a metric on this R. We'll be replacing this by D dash and this by D. So by continuity of f at x0, we mean for every epsilon positive, there is a delta positive such that D of x comma A is less than delta implies D dash of f of x comma f at A is less than epsilon. Okay, we replace this by the metric D here in x, D of x comma A less than delta. And replace this by the metric D dash in Y. So this D dash between fx and fa is less than epsilon. Okay, so between two metric spaces, you can generalize the concept of a real continuity of a real valued function of a real variable. Real valued function of a real variable at a point at a real number A of the domain set, which is known to be this by this general concept. You can generalize this to two different metric spaces. Okay, or this way. So this is what you mean by continuity of a function f at a point x0 belonging to capital X. Okay, right? And if f is continuous at each point of the domain set, we say f is continuous on the domain set capital X. Right? We say f is continuous on X if f is continuous at each and every point of it. Okay, that's how you define continuity on a metric space, right? And then, yeah, f is continuous or f is f from x to y is continuous on x. If and only f is continuous at each x naught belonging to capital X. At each and every point of capital X. Here you don't need to write suffix 0 because x is each, we are saying it is varying. Okay, so you don't need to put a particular value. So at each and every x of small capital X, this is small x. Yeah. This is small of capital X. Okay. Yeah. Now, in fact, you can show that this continuity is this property is equivalent to this property. F inverse of G is open whenever G is open in Y. See, F is mapping the X into Y. F is mapping X into Y. Okay, and here you are saying this one. See, corresponding to this epsilon neighborhood, you are able to find delta neighborhood. That means the F image that means the F image of this delta neighborhood of A is contained in epsilon disk of F of A. Okay, this f of x. If x is belonging to this one, this delta neighborhood means you have this one. If x belongs to this, it means the distance between x and a is less than delta. And the corresponding to fx, that is member in this epsilon. This is epsilon neighborhood of epsilon. This is epsilon neighborhood of fa. S epsilon of fa. Okay, so that's right. This can be written. Oh. Yeah. This can be, yeah, you can write this as, you bring to f to the right hand side. S delta of A is contained in F inverse of S epsilon of FA. Okay, right? So this, if you take the F inverse image of this epsilon neighborhood, it contains this delta neighborhood. Okay, out of this property, see, if you have continuity of F at x naught, you get this. The F inverse image of this epsilon neighborhood will be containing this delta neighborhood. Out of this, you can prove this condition. F from x to y is continuous if and only if F inverse of G is open whenever G is open. Okay. Out of the definition of continuity, you can obtain this. Okay. F inverse of G is open whenever G is open in Y. See here, you are taking G to be a subset of Y. G is open in Y means G is subset of Y. You are looking at F inverse G. You are looking for this G. You are looking at the F inverse. Okay. You are looking at F inverse. F inverse G will be subset. Here. Okay. By what is F inverse G by definition? This is set of all x belonging to capital X, as that f of x belongs to G. Okay. This is Y. This is X. Okay. This f is mapping x into Y, and this is some G. This is some G. What is F inverse of G? What is F inverse of G? It will be some, yeah, or some set. If you take a point here, x, and then fx will be mapped into G. Okay. Here, if you take x here, fx will be here. If you take x here, fx will be here. That's how you define F inverse of G. For this G, F inverse image will be set of all point x coming from capital X. So as the x comes from capital X, so that fx will be an element in G. Okay. For this, your f need not be onto. Or 1, 1, right? But still you can define this. Okay. Yeah. So we'll use this property to use this to answer this question. Okay, what is that question? What is that question? Show that, yeah. Show that f inverse of A is closed in X whenever A is closed in Y. To answer this, I'll use this property. That f inverse of G is open whenever G is open. I'll use this to answer that question. Okay, so let me draw this. Let me answer that question. So let f from X to Y be continuous. Okay, this is same as saying f inverse G is open. F inverse G is open in X whenever G in Y is open. Okay. Now, yeah. Let A contained in Y by close. Right? You take a closed subset of Y. Now look at F inverse A. You have to show claim. Of course. Yeah, I assume this. Yeah. We have to claim that, we have to show that F inverse A is closed. Claim F inverse A is closed. Okay. To show something is closed, you look at its complement. So look at F inverse A complement. To show something is closed, which will show its complement is open. So this can be shown to be equal to F inverse of A complement. Okay, so theoretically, you can show that this set is equal to this. Now, A is closed, so A complement is open. Now, I'll use this property. I'll call this star. So by star, this is open. Okay, I'm not proving this, I'm accepting it. Okay, I'm assuming it. So by this, F inverse of A, because A is closed, A complement is open, so F inverse of A complement will be open. Now, complement of this set is open. Therefore, F inverse of A is closed. Okay? Complement of this set is open. Therefore, F inverse of A is closed. I started with A closed and obtained F inverse of A is closed. Okay? This is F inverse of A. F inverse of A. Conversely, you assume F inverse of A is closed. Yeah. Conversely, let F inverse of A is closed for A contained in Y closed. Assume that this statement is true. Okay. Now we'll show that F is continuous, right? So F inverse of A is closed means what? You have to use this. So come into the terms of open sets. How can you come? If something is closed, its complement will be open. So this implies F inverse of A complement, is equal to F inverse of A complement. Okay, so F inverse of A complement is F inverse of A complement. So this is because we are assuming that F inverse of A is closed, its complement will be open. Okay, of course in X. Okay, right? A is here. A complement will be here. Its inverse image will be in X. Right? So because the set is closed in X. The set is closed in X. Its complement will be open in X. Okay. Now you use this property. If a set is closed, if a set is open in X, now F inverse of A complement is open. So A complement will be open in Y. Because, right? Because A is closed, so A complement is open. Further, what do we have? A is closed, so A complement is open. This also we have. A complement is open. A is open, A closed, so A complement is open. So we have F inverse of A complement is open, for A complement open. A complement is open, F inverse of A complement is open. So we'll use this property. Okay, and A is arbitrary. Okay, A is closed, it is arbitrary. So A complement open will be arbitrary. So that's how we have this statement. So from that we get that F is continuous. Okay, from here, right? This implies F from X to Y is continuous by star. Okay, your A is closed is arbitrary. So A complement open is arbitrary. So whenever A complement is open, you are getting F inverse of A complement is open. Therefore, from this property that you will obtain F from X to Y is continuous. Okay, so you assume that F inverse of A is closed, right? Yeah. You assume this statement and you are able to obtain F is continuous. Okay. So these two statements are equivalent. Okay. So here I would like to stop. In the beginning, I lost some 5 minutes, and this is very odd time, right? Odd time from 4 to 4:30 to 6. I don't know how much I could benefit you, right? So any doubts?
No, sir.
Hello? Hello? How
Sir.
many of you are no, active through all the 90 minutes? I don't know. Right?
Yes, sir, we are listening.
Right? I don't know, but you are bombarded with mathematics this morning, right? So can I stop here? Any doubts?
Sir, when will be our exams conducted?
Pardon? Your exams will be in June. That's what your that's what the COE was saying. I talked to him 2-3 days back. He said they are planning to hold in June. If you think they are too early, you can give a letter to him. Okay, to hold it a little time later. It's up to you. Okay, that's what I have known from the controller. They are planning to hold in June. Okay.
Okay, sir.
Anything else?
No, sir.
Can I stop here? Tomorrow we'll meet.
Okay,
Please
sir.
read.
Thank you.
Whatever I am doing here, you please read. Otherwise, you cannot understand. Right?
Yes, sir, we are writing.
Yeah. If you try to understand yourself sitting alone, then only you can learn mathematics. Otherwise, you cannot understand anything.
Okay, sir.
Right? Thank you.
Well,
Goodbye.
thank you, sir. Thank you, sir.
Goodbye.
Excuse me, sir.
Tomorrow we'll meet.